Hello ladies and gents, welcome to this webinar where we'll be focusing on design stage risk assessment using DesignBuilder's new uncertainty and sensitivity analysis tools. I'm Dave Cocking and with me today are Andy Tyndale and Nishesh Jain. Nishesh is a registered architect with over 5 years experience working as a sustainability consultant at PSI Energy, a green buildings and sustainable habitats design consultancy based in New Delhi. For the past 3 years, Nishesh has been involved in academic research at the Bartlett School of Environment, University College London. His current doctoral research focuses on energy model calibration, analysing and optimising energy, and indoor environmental quality in buildings. Nishesh has been heavily involved in the development of DesignBuilder's new uncertainty and sensitivity analysis tools as part of his research with UCL. You can submit questions at any point during this webinar via the questions box in the control panel. We expect the presentation to last around 45 minutes. And we've allocated some time at the end to answer as many questions as we can. The webinar is being recorded, so you can access it later if required. I'll now hand over to Nishesh, who will be the main presenter for this webinar.
Thanks, Dave. Welcome to the webinar on new uncertainty and sensitivity analysis tools released in version 6. In this webinar, we will introduce you to the new tool and understand its application for risk assessment in meeting performance targets through a case study building. The webinar is divided into 4 sections. First, we will discuss the background of uncertainty and sensitivity analysis, describe the process and its applications. Next, we will look at the case study building to understand the risk assessment problem and the need for uncertainty and sensitivity analysis. After this, we will show how DesignBuilder uncertainty and sensitivity analysis tool can be used for this purpose within the software interface, setting up the simulations and getting the results. Finally, we analyze the results and identify the lessons learned that can be communicated to the project team. First, the background. Energy simulation models are virtual representations of buildings and are used to predict their performance. As with any prediction tool, the inputs used are often unknown beforehand and are uncertain. Therefore, we tend to use a best estimate value for them. Uncertainty in the input variables can be due to lack of knowledge at design stage or unpredictable variability that can happen during construction and operation. These may relate to construction quality, user behavior, weather data, etc. Despite the best efforts in estimating the input values, it is often the case that the simulated results are very different from the actual performance, thus leading to and contributing towards the issue of the performance gap. While it is not possible to improve the estimates for inputs at the design stage, we can still determine the confidence level and the ranges within which their values would lie. For example, it is not possible to say that post-occupancy, the users will maintain the heating set point temperature at 20 degrees, as assumed by the designers. However, it is most likely that this value will be between ±2 degrees, with the highest probability that it will still be 20 degrees. Uncertainty and sensitivity analysis factors this in. Uncertainty analysis helps us to quantify the variability of our result based on the variation in the input. Therefore, instead of giving a single value answer, which is deterministic, uncertainty analysis gives us the various possible answers probabilistically, providing the likelihood of the most probable performance result. This is completely in line with the key principle of the methodology set out in SIPC TM54 that states that results should be presented as a range to illustrate the level of uncertainty around estimating operational energy use at the design stage. Sensitivity analysis then processes the uncertainty analysis inputs and outputs. It determines that out of the input variables, which are the most influential variables that cause the uncertainty in the output. Uncertainty and sensitivity analysis is a structured process and needs to follow a workflow. First step is to define the input variables. These must be defined as a range of values. Within that range, we have to define which values are more likely to occur than the others using probability distribution curves. For example, variables can be wall construction, operational set points, loads, etc. The second step is to define the analysis outputs. This is the result for which uncertainty and sensitivity analysis will be done. Depending on the purpose of the analysis, these can be either carbon emissions, net energy use, or cooling demand. Now, when the problem is defined, numerous parametric simulations are undertaken, sampling the input values based on their probability, and the requested output is reported back. When all the simulations are complete, output results are processed to calculate the uncertainty. To calculate sensitivity, outputs are compared with the inputs changed to analyze their interrelationship. Finally, based on the uncertainty and sensitivity analysis findings, input variable ranges can be defined to find good, less uncertain solutions. Some of the typical applications for uncertainty and sensitivity analysis include quantifying the effect of variation in inputs, such as understanding the effect of occupant behavior on building performance or the impact of poor construction quality. Undertaking probabilistic simulations to assess the risk in the building being able to meet its design performance objectives. Improve the optimization process by identifying and excluding unimportant variables from the search space. Support model calibration by identifying the main factors that lead to operation stage performance issues. In this webinar, we will be looking at how to use uncertainty and sensitivity analysis for risk assessment in meeting performance targets through a case study building. Now we will look at the case study building to understand the risk assessment problem. The 4-story office building is located in southwest England. It is highly insulated fabric. The building has many passive design features. It has high ceilings and narrow floor plates which are interconnected with atriums and cutouts. This leads to the building having deep natural light penetration and stack effect based natural ventilation. The building design has a focus on optimizing the fabric first. On the systems front, the building is naturally ventilated with manual and automatically controlled vents. Heating is provided with water-to-water heat pumps which are designed to recover heat from the main server room but are also backed up with supplementary gas-fired boilers. The comfort cooling is only provided in some meeting rooms. The designers have incorporated kill switches, which are master controllers to turn off building circuits from one control point. These can control and reduce energy wastage during out-of-hours use. There are also PV installations to reduce the net carbon emissions. The building is a flagship project designed to provide leadership in cutting carbon emissions changing the focus from design stage performance to operational performance. Due to this, the building was procured under a design and build energy performance contract, which required building to achieve an A rating under UK's Display Energy Certificate scheme, which compares operational performance of UK buildings against other similar buildings. This made the design and construction team responsible for energy performance of the building even during the operational stage. Achieving an A rating means that the building's net carbon emissions are at least 75% less than a typical office in the UK. This equates to just under 19 kilograms of CO2 per meter square per year for this building. This was made as the target under the energy performance contract. In these performance contracting projects, the contractual obligations for delivering certain performance targets require detailed risk assessment of factors that can lead to underperformance. Subsequently, mitigation and reduction measures of risk are needed to be identified and implemented. Generally, risk matrices are used in these type of projects. They track the risk areas using traffic light system to see which are the most important factors. Then those risks can be addressed at relevant stages of construction. Most of these risk matrices are qualitative based on experience and judgment. However, uncertainty and sensitivity analysis can help us to quantify that risk. Some of the risk factors identified by the designers in this project that make achieving the performance target difficult were potential issues that can arise from poor construction quality or value engineering of energy efficiency measures. There could also be problems in optimal control for HVAC systems, natural ventilation vents, or daylight and PIR sensors. Other factors included occupant behavior related issues, building user preferences, understanding of building operations, and potential increase in small power loads. Some measures to mitigate these risks were robust site supervision and detailed specification for mechanical and electrical services defined and finalized at the design stage itself. Additionally, post-occupancy aftercare and fine-tuning of building performance, along with having dedicated volunteers who would educate building occupants on how to use the building, were envisaged. Following is the condensed list of areas which were identified by the project team during the design stage and are relevant to the output objectives of meeting the desired performance target of 18.78 kilograms of CO2 per meter square per annum. These factors related to fabric, equipment, specification, and usage of building. To show that how these risk factors can be converted into design variables, I would explain them with a couple of examples. For instance, let us look at the risk related to equipment power density. Designers imagined that it is possible in future that the building occupants have more small power equipment connected besides their standard PC workstations. Additionally, there can be an increase in total occupancy with additional work desks being added. Both of these will lead to an increase in small power electricity use. The baseline target equipment power density is 10 watts per meter square. Now the task in defining this risk factor is a variable input to determine the range of variation and its probability distribution. As this is a user post-occupancy related factor, it is more likely to have a normal distribution. Based on past studies and discussions with stakeholders, the standard deviation in equipment power density was assumed to be 20%. The graph generated therefore will be a normal distribution graph with a mean value of 10. The standard deviation will be 2 meaning that 99% of the chances are that the building will not exceed a equipment power density of 16 watts per meter square. Now it is not possible that the value can be lower than the minimum equipment power density that is installed. The lower value of the probability curve therefore must be limited to the minimum installed equipment power. In this case, it is 8 watts per meter square, which means all values under this value should not be considered in the uncertainty and sensitivity analysis. So the final graph looks like this. I would like to highlight here that this is a continuous type variable in which when the values are sampled for parametric runs, they can assume any fractional value between the maximum and the minimum value in the graph. Another risk factor identified by the designers was thermal performance of the fabric. The reason I highlight this variable is because unlike the previous variable, this must be created as a discrete variable. In this building's context, due to poor construction practice or supervision, it was believed that it is possible to have the target U value of the walls not being met. To factor this risk in the assessment, multiple wall constructions are created with variation in the insulation levels and thermal bridging. The target U value is 0.15 watts per meter square Kelvin, and as this is highly likely that the wall performance would be poorer than being better, the lower value is 0.13 and the upper value is 0.28 with a distribution curve that would be skewed towards a higher value. Therefore, the distribution selected is binomial with more probability lumped towards the right. Unlike the previous continuous variable that can take any value between a range of numbers, discrete variables can only take specific values. In this case, external wall can only be one of the 8 options selected and no value between them will be used. More information on how and when to set up discrete variables and uniform continuous variables related distributions is available on the program help. Similarly, other risk factor areas that were identified as uncertain have been assigned appropriate distributions and ranges for use in uncertainty and sensitivity analysis. Now we move to the simulation model to understand how these variables were created in the DesignBuilder interface and how uncertainty and sensitivity analysis simulation run was set up. This is the case study building model that has been created as per design stage documentation. The 4-story building has 3 wings that are connected with corridors. If I go inside one of the floors, we can see that it is primarily an open office. The narrow depth of the floor and windows on both sides of the facade allow good daylight penetration. Also, we can see all floors are interconnected with cutouts and separated with virtual partitions. All this, along with high ceiling, form a part of natural ventilation strategy. In the activity tab, we can see that the activities in the building are assigned as per space type, primarily being open plan office. On the construction tab, all the baseline constructions of the building having high insulation and good airtightness has been defined. Data for lighting and other loads has been defined as per design assumptions. As specified earlier, the building system strategy of having heating and natural ventilation is defined with appropriate controls. Cooling is only in some of the meeting rooms. After the baseline model is complete, the first step in uncertainty and sensitivity analysis is to define the input variables and the analysis output. For this, we have to go to Uncertainty and Sensitivity Analysis Settings dialog. For users who have used DesignBuilder optimization before, the interface is very similar. Here we define both the input design variables and the uncertainty and sensitivity analysis outputs that we are interested in. First, we have to change the analysis type to uncertainty and sensitivity analysis. This will enable two tabs. One is for output definition and other is for design variables. Data on this tab for design variables is a summary of all uncertain design inputs which are the part of uncertainty and sensitivity analysis. Here, design variables can be added, edited, or deleted. The data shown in the table describes the user-defined name of the variable. The second column describes the variable type. These will be the type of input variables such as set points, loads, window to wall ratio, etc. Distribution category and distribution curve define the exact probability curve, whereas distribution summary provides the details of parameters that control this distribution, for example, the mean, standard deviation, etc. Target objects define the scope of the variable, that is, if the values are changed for the whole building or selected zones or elements. Settings on the right-hand side info panel are used to add, edit, or delete a variable. We have already added most of the design variables that are present that represent the risk factors. But as an example, I will show you how to create a couple of more design variables that we discussed earlier. For this, the risks rated were related to extra equipment use and other was regarding uncertainty in wall construction. To create a new risk factor, I will add a new variable. This dialog is used to define or edit design variables for uncertainty and sensitivity analysis. First, we must select the appropriate variable type and distribution curve. Then, based on the distribution curve, we define its parameters and or transform its shape. The resultant graph can be visualized after every change has been processed and pressing the create graph, update graph button. For our first risk factor, if we remember, the variable was equipment power density having a normal distribution of a mean value 10 and standard deviation 2. So I will look for the variable type equipment power density under the internal gains and lighting folder in the variable type list and select it. Now I will define the rest of the distribution parameters. The distribution curve is normal, mean value is 10, standard deviation is 2. Now I can visualize the graph to see how it looks. If we remember that we excluded the values under 8 watts per meter square, as this is the minimum load which will always be there in the building. For this, we need to truncate this distribution. I will define this value under the truncate lower side. I will visualize the graph by creating update graph, and the graph now created is as desired, so we can close the dialog. This new variable has now been added to the list. Now for the second risk factor we discussed was wall construction. The risk was poor thermal performance of the fabric. The concern was that due to poor construction practice or supervision, it is possible that the target U value might not be met. I will add a new variable again. This variable is related to construction assembly, and the variation in U value of the wall must be represented as separate construction assemblies. This makes this variable a discrete variable where a specific number of construction items are created and selected as options in the analysis. To add this variable, I will look for variable type external wall construction under the constructions folder, and I will select it. Now I might select all the various wall constructions that can represent my uncertainty. The target U value of the wall was 0.15 with a upper value of 0.28 and lower value of 0.13. To represent this range of deviation, the users need to pre-create their different constructions and have them available in the construction library. For this, I have created 8 different constructions options which range from the upper bound to the lower bound to upper bound value. The modification of the U value was done by changing the insulation thickness, which is a most likely defect. You can see in the insulation thickness was modified, and different constructions were created with different U values. I will select all the constructions which are required and press OK. After selecting the options, it is important to order them so that they match the intended probability values for each selection. This could be done in an increasing or decreasing order. I will reorder the constructions in increasing U value by selecting and moving each option. I will check if the order is correct, and then after that press OK. To check if the distribution the external wall constructions have been selected properly, I will create the graph to see these values. The graph has a default uniform distribution. However, as it is more likely to have a poorer U value than a good one, distribution curve needs to be skewed towards a higher value. To achieve this, I will change the distribution to binomial and change the probability number to a value that will most closely describe the variation. You can play with the probability number till the time you reach the desired shape of the graph. Once we are satisfied, we can see that the created graph is as desired. More information on how to generate these options for various variables related to constructions and other selection items is covered extensively in an advanced uncertainty and sensitivity analysis tutorial on the program help. This new variable has now been added to the list and our input variable definition is complete. The second step in setting an uncertainty and sensitivity analysis run is to select an appropriate output. I will go to the Output tab. For our case, the target is related to carbon emissions. We will use operational carbon emissions as the output. To add an output, go to Add Output button and select the appropriate analysis KPI. There are multiple KPIs available. However, as the correct one is already selected, I will just name this. Now, uncertainty and sensitivity analysis setup is complete. We can close the dialog. To start the analysis now, we have to go to the simulation screen. On the simulation screen, before any uncertainty or sensitivity analysis is done, we need to do a baseline simulation run. As this is a large model, I have already done a baseline analysis which I can load using the simulation manager. I go to the simulation manager and I select the desired run and load the results into DesignBuilder. DesignBuilder Simulation Manager allows us to run and control multiple parallel simulations and access the results. The Simulation Manager stores the simulation results. The results can be accessed in any compatible model at any other time. It is a convenient way to store, access, and compare simulation results either via Results Viewer or by loading results into DesignBuilder main application. Using Simulation Manager, simulations can be run on a local machine, local network, or the cloud. As the baseline results are loaded, if I am satisfied with the model, I can now set up the uncertainty and sensitivity analysis run. For this, I must go to the Optimization plus UASA tab. To start a new calculation, I need to press Update Calculate button. In this calculation options dialog, we define the parameters for the simulation run. The dialog is divided into three sections: the settings selector, the graph window, and the simulation grid. All the settings are defined on the left, and once the simulation is started, after each set of the runs, a histogram graph is populated in the chart on the right. The input variables sampled and the outputs simultaneously get populated in the table below. This continues until the requested number of runs are complete. For uncertainty and sensitivity analysis, the two important settings that need to be done here are first, the sampling option, and second, number of runs. There are various sampling options available and have been implemented in DesignBuilder. Program help can be used to understand the applicability and limitations of each of them. We are using Latin hypercube sampling for this simulation as it is an efficient method and can cover a large search space even with relatively small number of runs. The number of runs requested will depend on both the number of variables selected and the sampling method. In this case, the simulation run has 10 variables, and as a rule of thumb, for Latin hypercube sampling, 10 times the variable number should give reasonable estimate of the population mean. This means 100 simulations should be enough to identify the less important variables and screen them out. However, as we are doing this analysis for risk assessment and we are also interested in more accurate estimation of overall uncertainty, therefore, to increase the robustness of the calculation, I will use a value of 200. And then after the settings are complete, I can press start to start my analysis. This simulation will take a long time to complete. So I will switch machines to the one in which I already have simulated this model and the results are complete. This is the model where we have completed the requested 200 simulation runs for the uncertainty and sensitivity analysis. Once all the simulation runs are complete, the calculation options dialog will populate with the histogram of the spread of the results on the right hand side and the table with all the iterations and their input settings which were changed at the bottom. I can close this dialog to see uncertainty and sensitivity analysis results completely in the main results screen. The main uncertainty and sensitivity analysis results screen shows the same histogram and the results grid. However, now with histogram controls located in the display options on the left, we can modify and analyze the uncertainty spread in more detail. We can redefine the bin ranges, bin widths, and bin numbers. The summary statistics box on the right of the graph provides a 7-point statistical summary of the analysis. This is useful to quickly understand the overall variation in the results. For this simulation run, we observe that the uncertainty in carbon emissions have a more than 10% standard deviation, and excluding the outlier values, the worst performance is 60% more. More detail on this with infographics and tutorials that analyze such results has been covered extensively in program help. While uncertainty analysis represents the spread of the output, sensitivity analysis provides us detail of which inputs are the most important. To see the sensitivity results within the display options, I can change the analysis from uncertainty to sensitivity. Sensitivity analysis results show that the most important factors that contribute to uncertainty. By default, the sensitivity analysis results are ordered in decreasing order of importance, decided by the standardized regression coefficient value. Higher the absolute value, higher is the importance. Positive value shows that there is a direct relationship, and the negative means an inverse relationship. In other words, positive value means that increase in the variable value increases the output and vice versa. For this analysis, most important factors that are related to systems and uncertainty in operations and loads. Being a naturally ventilated building, air tightness is a big issue and can contribute towards lower performance. This is because due to operable windows in naturally ventilated buildings, sealing around the opening requires significant care and attention. Additionally, the risk we discussed regarding equipment is also very important and requires control. As far as fabric is concerned, the envelope U values do not account for more sensitive outputs because envelope is already highly efficient and other factors are more influential. Besides this graph, DesignBuilder can also generate an uncertainty and sensitivity analysis report. To create a report, I can change the display result option from graph to the report. This report is very informative document that summarizes the entire uncertainty and sensitivity analysis simulation result. The numbers that are not intuitive to understand are explained in detail to assist specialists and new users in interpreting the results more meaningfully. Report is divided into 4 parts. The first 2 parts describe the outputs. As a sanity check on the parametric process, the third part provides the analysis summary and details about the sampling if the sampling of variables was done as per user request. In the sensitivity analysis report, this section also contains the uncertainty results. Most importantly, in the last part of the report, we provide information interpreting the results of the graph and statistical details by identifying most influential parameter for each output. In the first part, all the input distributions are redrawn and their details are mentioned. Then we can move to the second part, which would list down all the different outputs which we have requested. In this case, there was one. The third part details analysis summary. This details all the input samples that were created and the output uncertainty, that is the uncertainty analysis. At the end of the report, the results numbers for sensitivity analysis have been analyzed and interpreted. Numbers like standardized regression coefficient, p-values, r-squared values, etc. are interpreted in plain English, and most important variables are ranked and highlighted in color codes. I will be using and explaining these when we move back to the presentation. The graphs and the report can be exported as image and documents. Additionally, the raw simulated data can also be exported as a CSV file. This is extremely useful in cases where further analysis or post-processing of result is required in specialist statistical packages. As the objective of uncertainty and sensitivity analysis is to assess the normalized carbon emissions against an energy performance contract target, I have processed this data in Excel and presented the results. Here I will present the analysis of DesignBuilder uncertainty and sensitivity analysis results in the context of this risk assessment problem of meeting performance targets in the energy performance contract project. As discussed earlier, initial design stage uncertainty shows a very wide range of variation. In this histogram, I have normalized the bins to emission values as per performance target units. The target value was 18.78, which lies somewhere here. Looking at the spread around the target value, within the assumed uncertainty scenarios, it is easier to underperform and miss the target. The chances to meet the target are only 25%, and 75% chances are that the building, when operational, would not be able to perform as desired. Therefore, to ensure that the performance target is met, the baseline values for some variables need to be reduced to move the entire graph to the left, and uncertainty in most important variables need to be reduced to reduce the overall spread in the graph. This will increase the chances of the building meeting the performance target. Sensitivity analysis results provide us details for the most influential variables. As taken from sensitivity analysis report, the list sorts the variables in decreasing order of importance. Green factors are most critical, yellow are moderately important, and the red ones are the least sensitive parameters for that output. As analyzed earlier, sensitivity results show that infiltration, small power, and other system and user behavior related factors are more important in this building and need to be controlled. The envelope U value does not account for more sensitive output because the envelope is already highly efficient and other factors overpower it. Based on this result, mitigation measures identified in the risk matrix for reducing infiltration, improving system efficiency, etc., can be highlighted and implemented more robustly. Based on the feedback received from various uncertainty analysis, modifications were done in the project to have controls over load ratings of equipments and lighting being used, system specifications finalized and vetted at the design stage, separate vents with good sealing were installed, provisions were made to implement soft measures for occupant education by the building owners. With a more robust commissioning and commitment to implement and preserve many energy efficiency measures, the probability of meeting the performance target was more than doubled, increased to more than 66%. So in conclusion, uncertainty analysis in this building helped to understand the spread of building performance under various model output variations. In case the performance contracting like this, these provide insights into what are the chances of the targets being met. Sensitivity analysis identifies the most important variables and therefore can help them in design decision making for safeguarding most critical input parameters from high degree of variation. In this case study building, many risk factors were assessed and potential issues relating to air tightness in naturally ventilated buildings, uncertainty around user behavior, and system performance were identified and then managed, thereby increasing the chances of meeting the performance targets. Uncertainty and sensitivity analysis can therefore be usefully used in risk assessment for design stage performance prediction. Understanding these results can provide designers and building managers insights into low-hanging fruits, that is, areas where it is most beneficial to deploy more resources, time, and effort to get the best results. This is the end of the formal presentation. Thank you.
Okay, thanks Nishesh. That was a really interesting presentation on a topic that I'm sure will be new to many of the people in the building performance simulation industry. For those listening and watching, we really do hope that you found it interesting and informative, and we also hope to hear from you and to hear how this new functionality helps you to de-risk and improve confidence in your future work and projects. We are planning a follow-on webinar to show in a little more detail how uncertainty and sensitivity analysis can be used to improve the building or the process around building optimization studies. So thanks for listening. That's the end of the formal presentation, but we will stay live for another few minutes to take any questions. There'll be a brief pause now whilst we review any questions already submitted, and we'll start answering those very shortly.